Welcome to Mathematical Analysis. Today, we are going to explore one of the most powerful tools in calculus, Taylor's theorem with remainder. If you have ever wondered how calculators compute complex functions like sine or logarithms so quickly, this theorem is the secret engine behind it. Let us dive in and uncover how it works. Now that we know what we are studying, let us understand why it matters. Imagine you are building a curved roller coaster track, but you only have straight pieces of wood. You can roughly match the curve, but there will always be a tiny gap. In mathematics, we do the exact same thing. We replace complicated, hard to calculate functions with simple polynomials made of basic powers. Taylor's theorem gives us the exact recipe to build this approximation. But because a simple polynomial is rarely perfect, there is always a leftover piece, which we call the remainder or the error. Building on that roller coaster analogy, let us look at the mathematical equation. The theorem states that any sufficiently smooth function, which we call f of x, can be split into two distinct parts. The first part is p sub n of x, which is our nth degree Taylor polynomial. This is our simplified algebraic guess. The second part is r sub n of x, the remainder term. This represents the exact mathematical error between our guess and the true function. If we want to know how accurate our polynomial is, we must understand and calculate the size of this remainder. To understand how we get that guess, let us break down the polynomial part. This long formula shows exactly how we construct the approximating polynomial around a specific center point, called a. We start with the height of the function at a. Then we add the first derivative, which gives us the starting slope. Next, we use the second derivative divided by 2 factorial to match the curvature. Each subsequent term uses a higher derivative to make the polynomial hug the true function more tightly. We are essentially building a fake function that behaves exactly like the real one near our starting point. Before we move on to calculating the error, let us see this visually. Look at the solid black curve representing our true function, f of x. Notice how the dashed lines representing our Taylor polynomials start to hug the black curve around the origin. The first degree polynomial is just a straight tangent line. The second and third degree polynomials bend to match the curve much better. But look at the vertical gap between the true function and the polynomial at a given point x. That exact vertical distance is our remainder, r sub n of x. Now that we have seen the gap visually, we face a practical problem. We cannot calculate the exact error without knowing the exact function value, which defeats the whole purpose of approximating. Because of this, we use special formulas to estimate the remainder instead. There are 3 major ways to write this remainder: Lagrange's form, Cauchy's form, and the integral form. Each is useful for different types of mathematical problems. Lagrange's form is the most common in engineering, while Cauchy's form is a powerful backup tool for tricky mathematical proofs. Let us look at Lagrange's form first. This brings us to the most widely used error formula, Lagrange's form of the remainder. Notice how it looks exactly like the next term in the Taylor polynomial sequence? However, there is one crucial difference. Instead of evaluating the derivative at our known center point A, we evaluate the n plus 1th derivative at some mysterious unknown point, C. This point C is guaranteed to exist somewhere strictly between our starting point A and our target point X. Because we do not know exactly where C is, we find the maximum possible value of this derivative to determine the absolute biggest mistake our approximation could make. While Lagrange's form is great, sometimes we need an alternative, which leads us to Cauchy's form of the remainder. This formula also relies on that unknown point C located between A and X. It looks a bit more complicated, but the symbols mean the same things. We have the n plus 1th derivative evaluated at C and n factorial in the denominator. We use Cauchy's form primarily when Lagrange's form fails to prove that the error shrinks to 0. It is an incredibly powerful backup tool, especially when dealing with the binomial expansion of fractional powers in advanced proofs. Having these formulas leads us to a critical question. If we keep adding more and more terms to our Taylor polynomial, does the approximation eventually become perfect? We want to know if the remainder shrinks down to exactly 0 as the degree grows toward infinity. When this happens, it is called convergence. The finite polynomial transforms into an infinite Taylor series that perfectly equals the original function. If the error disappears as we add more pieces, our fake polynomial track becomes completely indistinguishable from the true mathematical curve, and we can safely use it for any calculation. To guarantee that perfect match, we rely on this simple limit equation. It is the ultimate goal of Taylor series expansion. It states that as the number of terms n gets infinitely large, the error term r sub n of x becomes infinitely small, eventually hitting 0. When this limit is 0, the approximation is no longer just an approximation. It becomes an exact representation of the function. We must always check this limit before assuming an infinite Taylor series is valid. If the error does not vanish, the infinite series will give us completely wrong answers. Let us see this in action with a practical example. Suppose we want to approximate the mathematical constant e, which is roughly 2.718. We will do this by evaluating the exponential function at x equals 1. We will use a third-degree Taylor polynomial centered at e equals 0, also known as a Maclaurin polynomial. The exponential function is wonderful because its derivative is always exactly itself. So, when we evaluate the function and all its derivatives at our center point of 0, we simply get e to the power of 0, which is 1. With our derivatives calculated, we can now build our polynomial. We substitute our derivatives, which are all 1, and our center point of 0 into the standard Taylor polynomial formula up to the third degree. The factorials in the denominators are 2 factorial, which is 2, and 3 factorial, which is 6. This gives us a simple algebraic equation, 1 plus x plus 1/2 x squared plus 1/6 x cubed. This simple equation mimics the behavior of the complex exponential curve near 0, using only basic arithmetic operations that any computer can easily process. Now that we have our polynomial, let us plug in our target value. By substituting x equals 1 into our equation, we get a simple sum of fractions, 1 plus 1 plus 1/2 plus 1/6. Adding these together gives us 8/3, which is approximately 2.6667. Our polynomial approximation tells us that e to the power of 1 is roughly 2.6667. We know the true value is about 2.718, so our guess is fairly close, but it is clearly not perfect. Since our guess is not perfect, we must figure out the maximum possible error. We use the Lagrange remainder formula for n equals 3. This means we need the fourth derivative evaluated at some unknown point c, which must lie between our center of 0 and our target of 1. The denominator is 4 factorial, which equals 24. Because the function is e to the power of x, the fourth derivative is still just e to the power of x. So we plug in c to get e to the power of c in the numerator. To finish our error calculation, we need the biggest possible value for e to the power of c. Since c is between 0 and 1, the largest it could possibly be is e to the power of 1. Even if we do not know e exactly, we know for an absolute fact that it is less than 3. Therefore, we replace e to the power of c with 3 to find the absolute worst case scenario. Dividing 3 by 24 gives 0.125. This proves mathematically that our approximation is off by no more than 0.125. So, we have successfully approximated a function, but this brings us to a dangerous trap. It is very tempting to believe that if a function is smooth and we can take its derivatives forever, its Taylor series will always eventually match the function perfectly. However, there are strange pathological functions where the Taylor polynomial can be calculated, but the remainder term never shrinks to zero, no matter how many terms you add. In these cases, the infinite Taylor series converges to a completely wrong answer. Let us look at a famous cautionary example that proves this point. Here is the mathematical formula for our cautionary example. Consider this highly unusual function, defined as e to the power of -1 over x squared for all values except 0. To make it continuous everywhere, we explicitly define the function's value at 0 to be 0. This function is incredibly flat right at the origin. In fact, it is so flat that if you calculate its first derivative at 0, you get 0. Astonishingly, if you keep going, every single derivative of this function at x equals 0 is exactly 0. Let us see what happens next. Let us try to build a Taylor series for this unusual function. Because every single derivative at the center point of 0 is exactly 0, every single term in the Taylor polynomial becomes 0. Therefore, the entire Taylor polynomial for this function, no matter how many terms you add, is just a flat horizontal line at 0. The polynomial is simply 0 everywhere. But if you plug any non-zero number into the original function, like x equals 1, the true function value is e to the power of -1, which is definitely not 0. Because the polynomial is always 0, let us look at the remainder. The remainder must equal the entire original function to make the equation balance. As we let the degree n go to infinity, the remainder does not change at all. It stays exactly as e to the power of -1 over x squared. The error never shrinks to 0. This proves that just because you can write down a Taylor series does not mean it actually represents your function. The remainder is the ultimate judge of whether the approximation is mathematically valid and safe to use. After seeing both successes and failures, let us understand why this matters in the real world. Taylor's theorem with the remainder is the invisible engine powering almost all modern computational technology. When you type a trigonometric or logarithmic function into a calculator, the machine does not look up the answer in a giant table. Instead, it uses a Taylor polynomial to calculate the value using only basic addition and multiplication. The remainder term is crucial because engineers use it to figure out exactly how many terms are needed to guarantee the answer is correct to 10 decimal places. We have covered a lot of ground today, so let us review the key takeaways. First, Taylor's theorem allows us to break down complex, difficult functions into simple polynomial approximations. Second, the remainder term is the exact measure of the error introduced by this simplification, and we can estimate it using forms like Lagrange's or Cauchy's. Finally, we must always check that the remainder shrinks to 0 to guarantee that an infinite series truly converges to the original function. Without this theorem, modern numerical computing and simulations would be entirely impossible. You now understand the foundation of computational mathematics.